So, hi everyone. I'm Pascal Fecht. I'm coming from Fecht in Germany. And before getting started, I would like to introduce myself. So, I'm a software developer at Innovex. And to keep it short, I recently finished my master thesis in transfer learning for NLP with a focus on text summarization, which is mainly the baseline of our solution. And before getting started, I would like to thank three more people. First, my supervisor at the university, Professor Maucher, and as well as my supervisor at Innovex, Hans-Peter Zorn, and the third, my colleague, Sebastian Blanc, who made mainly the adoption to the Swiss text data set. So my master thesis was on the English data set, and he did the pre-processing and the adoption to use it in my solution or my model or my setup. But I will explain this in more detail in a second. So to get started with the approach and implementation, we mainly focus on what's the content of the keynote beforehand. So we put a lot of our main contribution is on the embedding layer. So we try to find a better meaning of words to improve the quality of summaries. So if we have it in this step, so we can see we have an input data, which is in our case a document, so German with German words. And we have to bring it in a numerical representation. So we learned a lot of embeddings beforehand. I don't have to go too much into details here. We used word embeddings, so we didn't do subwords or something else. And we feed these embeddings to a summarization model, which creates short, dense representations of the input. And the summarization model in our case is the Copulate model, which I will explain to you in a second. So to give you a bit of our workflow, so the main idea is not only to use word embeddings. So in our case, we use pre-trained German glove embeddings of a dimension of 300, and these embeddings have the word meaning in it. So as we learned beforehand, we have only one unique representation of each word, and it may be beneficial, or it's definitely beneficial to have a context of words. So words have different meanings in different contexts. And this is the reason why we also chose multilingual word embeddings to also have this contextual information. So we have on the one hand side the word meaning, and on the other hand side the contextual information. And we combine these two because we found out that it's beneficial to further benefit the word embeddings. So not only feed the word embeddings to word and just use the result of word, but combine them both. And we, as I said, we concatenate these and feed it to our summarization model, which creates the summaries. And to take a look on the summarization model, it's quite similar to the one we've seen before. So we use an encoder-decoder model. The encoder reads the input document, creates an intermediate representation, and the decoder starts to generate summaries word by word. And we also use attention, so to further benefit the decoder to not only have one fixed length vector representation of the entire document, but to also learn to attend to different words, different parts of the input at each decoding step. And as mentioned beforehand, in summarization models, we often have the problems of very long documents, so we have very long context, hundreds of words, and this is why we typically use something like a copy mechanism. So in the Copulate model, it's a different implementation of the pointer generator as we've seen beforehand, which just allows us to look back to the input sequence and to copy words that are not in the vocabulary or are meant to be important for the summary. And the model itself is bidirectional LSTM from Gu et al. From 2016. Bidirectional LSTM encoder and LSTM decoder. Short note on the implementation, since I have a software engineering background, I'm like interested in how to actually implement something like this with a framework to get reproducible results. And we used LNLP for this. It's based on PyTorch, and what it basically does, it helps us to structure code, and it predefines components like for the training. For example, we can define a config file, which is a JSON file that has configuration details like what model do we want to use, how long do we want to train, what embeddings do we want to use, and all that stuff, and we feed it to a trainer which does the iterations and all that stuff, so we don't have to implement this from scratch. And we also get some things like logging or a TensorBoard to get immediate feedback, and we store our best model. So we define a metric, how to say what's the best model. So in our case, it's just the lowest negative log likelihood, and we keep this model to use it in the second step during inference or during testing with the predictor to create actual summaries or metrics like the root score. So yeah, that's turned out to be pretty useful to compare different experiments during my master thesis and now as well, since we could just change the data set to a German data set and use the rest out of the box. Preprocessing, we didn't do that much for German, so we just took 80% for training, 10% for validation, 10% for testing, and we trimmed it to a length of 400 words of the document, 100 words of the target, just because on the English data set it was the same, so we didn't really think about is it useful or is useful information on the end of the document. We just kept it like this, and we also used the vocabulary of the 50,000 most frequent words in German, which turned out to be having some disadvantages, as I'll show in a second. And as well, we just did white space tokenization. We didn't do something else in the preprocessing step. Our results, two observations. So the candidate summary is the generated summary, and the reference summary is the one we got. So the goal target. And for everyone who's not speaking German, so it's like the summary of an ice hockey player, and the model recognized that it's important to mention that he actually is an ice hockey player and where he's playing. But somehow the model didn't recognize that he moved to a different team. So the model knows what's important to mention in a summary, but it's like the fact is wrong, so he moved to a different team. That's something we recognized a couple of times, which is really interesting. And a little bit more basic, what's happening a lot in our summaries, that we have unknown tokens. That's just because our vocabulary size is fixed and we didn't do pre-processing, and the copy mechanism didn't really, in English we didn't have this problem at all. It's a German problem because compound words and stuff like this. So the copy mechanism didn't solve this in general to really copy a word instead of generating unknown token. So we have around 3.5% unknown token in our summary of the words. And to show the root score, so that's the English root score. We didn't do anything special for German. It's a little bit lower, you've seen it before. Root score, for everyone who doesn't know it, or it's just a comparison between our summary and the goal target. So that's also one problem in text summarization in general. We only got one goal target, but you can express a text in very different meanings, very different ways. But we also always try to optimize it for a single goal target. And that's the only really well explored how to compare text summarization. And as you've seen, like unknown tokens are considering the root score not too bad, but reading the summary like by hand, it's pretty pretty bad. And the second one is the copy rate, which just takes a look on our generated summaries on each word and checks if it's already in the document, so given in the article. And the idea behind this is that we want to build an abstractive system, and if we copy 100%, for instance, of the token, we didn't like generate words from our own language understanding, our own language model. And we got a bit more than the reference, but still under 80%, what is, from my experience, a pretty good value. But still, keep in mind we have 3.5% unknown token, which are obviously not in the source document. To summarize our work, we have some kind of contextual sequential transfer learning, which means that we pre-train a bird and apply it to a different task. So we didn't do transfer learning from to different domains, for instance. So we didn't train text summarization on news article and applied it to Wikipedia, but we trained a model, or we used a pre-trained model and applied it to text summarization. And we have a reusable implementation where we can change the actual model, summarization model, and the embeddings. But we still have too many out of vocabulary words, and we didn't use reinforcement learning, so the root score during training to further benefit the generation of text summaries, and we didn't use coverage, which creates repetition. So that's something you've already seen before. So that's it. If you have any questions, feel free to ask.
I didn't understand why your copy mechanism cannot handle all these.
So yeah, that's after like I finished my thesis, I recognized like this is a different implementation from the pointer generator. And it's basically, it separates completely between either saying I copy from the source or I take a word from the predefined vocabulary. And if it's like on the one side, it doesn't switch again. So like the problem is you either say I want to copy or I want to generate, and generate means also out of vocabulary, or if I don't know, if it's not in the predefined vocabulary. So it's more about, did you understand?
But you could enforce that you
that's
avoid all these.
Probably with longer training times, or like larger vocabulary, or like preprocessing or something like that. So, or just like in the model some changes to further benefit the copy mechanism if we have the moment. Yeah.
Have you measured how much it helps to concatenate the glove embeddings to the bird output?
Yeah, not exactly on. So on in my master thesis, it was it's more beneficial on less extensive data sets. So if you have like in this example 100,000 of data, it's more beneficial than having 300,000 of data like in CNN Dating, for instance. So we in the beginning we used cloth embeddings only, and we achieved like 1 to 2 point more root score. But it's not that much, and we didn't fine-tune bird embeddings, so we kept them as they are. And yeah. Any further questions? Thanks for your attention.